Hi everyone, I'm excited to welcome you to today's webinar, Advanced Optimization Techniques, Managing CSO Spill Count and Risk with Confidence. The focus of this webinar will be how to reap all those benefits of optimization for catchment strategy planning, whilst directly including the now essential TSR metrics such as annual spill count. Today, it will be our Senior Project Engineer Ben to take us through how we have reduced those complex annual TSR metrics such as spill count into quick running simulations, in order to find those detailed solutions to all performance needs of the most difficult catchments within a single 4 to 6 week study. From this, we will look at how we have developed accurate, efficient metrics to prove the business-wide investment required, cost-performance trade-offs to justify going beyond the legal minimum requirements, and communicating catchment strategies to give a head start to stretch design teams. Ben, would you like to introduce yourself?
Thanks, Karen. I'm Ben Sims, a Senior Product Engineer at Engisoft UK. So perhaps though educated as a mechanical engineer, I've now had several years experience applying optimization and automation techniques to various things in the water industry, mainly working with experts from water companies and consultants, along with us in Engisoft, to develop new tools and processes, such as the one we're going to be presenting today, to solve key industry issues.
Thank you, Ben. Before we get started, just a reminder that you have been muted for the efficiency of today's webinar, but feel free to use the chat box to ask any questions that you may have throughout. We'll endeavour to cover as many questions as we can at the end of today's Q&A section. Let's get started. Back to you, Ben.
Thank you for the introduction, Karen. So yes, as she said, this is primarily interested in the overview of the advanced optimization methods and how those kind of time series metrics can be directly included in such an optimization study to support business planning. We will have, of course, begin with a bit of background on the issue and surrounding challenges we're aiming to solve, then move on to the method in a relatively high level, but hopefully still covering the key steps in enough detail so you can visualize what we've done. Then, of course, the most exciting part, an example of the typical results and how they can be used. As obviously very large data sets are generated from these kind of things, and need a bit of thought as how best to convert that into visuals that can be understood. And then we'll finish off with a quick summary of the outcomes and benefits of the optimization approach. So let's get started on the challenges. Over some time, we've been working with a number of UK water companies facing similar challenges. Mostly surrounding the ever-increasing demands that are being placed on wastewater networks. And so there's a need to decide where to invest upgrades in the most efficient way to achieve the performance requirements still. Obviously a high level of uncertainty around a lot of these things, with major factors of growth and climate change in particular. The key performance targets that must be met are also becoming more complex, with more focus on annual and longer time periods, and it must be done ever more efficiently, as we're already expecting a sizable increase in the investment required, so we don't want to add waste on top of this. And of course, to satisfy regulators, the water companies will need to give them an accurate and confident understanding of the costs to achieve the kind of legal minimum requirements, and prove it to the regulator on a catchment they're not familiar with. If they want to choose to go above and beyond those minimums, they need to be able to give an understanding of the cost versus performance trade-off to achieve any enhanced performance. And of course, develop high-level sort of catchment solutions and give confidence that these will build into a long-term plan and aren't in any way potentially wasteful and might be redundant in the future. And of course run all these analyses as fast as possible to meet the tight deadlines and put these interventions in the ground as soon as possible. So water companies have explained several key issues with existing analysis methods. Typically complex catchments just feature too many individual flood and spill locations and possible solution options to evaluate them all individually. So perhaps for business planning type studies, only very high level summary results might be possible within the available timeframes, creating rough solutions which therefore don't have very accurate costs. It might normally balance out across the company, but it'd be quite helpful if we could test options closer to that buildable level and reduce the business risk. When we need to get to developing more detail, the process is typically quite reactive, considering issues in isolation and testing only a small number of solution options for each. And of course, this brings with it issues with auditability. Solutions you may not typically evolve based on human experience. It's not necessarily easy to document the process that led to that decision, or it's not particularly repeatable. And there's always that question of, what if we were to try this or that extra idea? Could it be a bit cheaper than what we've already got? It's always difficult to be sure that the solution you've got is truly the most cost-effective possible. We typically just have to get as far as we can before the deadline approaches and we've got that feasible performance achieved, and then we have to just accept the solution we have at that point. However, in the recent past, both others and ourselves have presented methods for catchment-wide optimization, and this can get us quite a fair way to helping with some of those issues. We can allow humans to focus on what is truly valuable, i.e. defining the problem and making the complex engineering decisions based on results and data, whilst allowing the automated optimization processes to fully explore the detail and the complexity of upgrading several thousand assets potentially across the catchment and solving lots of issues in one go. We can get Pareto fronts, or simply just basic cost versus performance or other objectives traded off against each other, directly giving us one of those things that would be very helpful to be able to present to the regulator. And it's very easy to have multiple trade-offs for the different uncertain input scenarios. And of course, given the large data sets that are developed, we need the kind of advanced analysis tools to convert those large data tables into some graphics or maps, which can be used to fully understand the data and obtain useful findings from it. However, traditional optimization approaches have all usually focused on using short duration design storm type events because of the need to run several thousand simulations, which is of course not compatible with the latest industry needs to include those time series metrics such as spill count. So together with water companies and other consultants, we furthered these optimization methodologies to meet these needs and include the regulated metrics from 1 or 10-year time series simulations. There's a few sort of key items that form part of this new process. So the first is ensuring we're using the most efficient, most advanced, the best-in-class optimization algorithm that we can, which reduces the number of iterations we need to fully explore all of the options available to us, and that allows us to have longer simulations per design and keep the total runtime at a sensible level. We also use extract events, so rather than running the full time series, we extract the critical parts from that. So we developed a tool in order to do that, which can then make a good approximation of those full time series events to run the actual optimization on. And then once the optimization is complete and we have the results, we can verify a few of those best designs back on the full simulation to ensure the results are accurate and give us the confidence we need. Okay, let's move on to take a look at the methodology in a bit more detail. So in case there's any here perhaps less familiar with the optimization approach, it can be a little different in philosophy to perhaps a traditional manual method. So we begin by defining the study. We list all feasible upgrades, even if we're not sure if they might be beneficial or not. We'll let the algorithm decide that later. And we define all the performance goals and targets we want to look at. We'll add in all the constraints that are relevant, even if they're not necessarily the primary target we're looking at. It's worthwhile considering everything in the catchment in one go. We can then build the optimization logic in the software and then run the study. It will explore all the different possibilities in one go and produce a large data set of results which can then be analysed to fully understand the results of that. We'll then use smart interactive reporting tools to make well-informed, confident investment decisions. Now, when it comes to optimizing for spill count or other such annual metrics, there's a couple of extra steps to wrap around that process. It's usually not feasible to run the full 1 or 10-year simulation for the 1,000 or so iterations required, even with the best algorithms. It would just take months to run. Therefore, we usually begin by running a tool we've created to extract the critical periods from those long events into what we call the extract events. As well as spill count, we've got methods for including like worst dry day, full flow to treatment, annual storm tank utilisation. I'm sure other metrics could be added in similar ways. The optimization is then run only using those shorter events, so it can run relatively quickly. And then when complete, we take a selection of the optimal solutions from the optimization, the ones we're most interested in potentially building or presenting to the business case, and then rerun those on the full 1 or 10-year simulation as a back check, and just verify the results from those extract events are accurate. In most cases run so far, the results match sufficiently well as is. But in a few situations, there's been some discrepancy, which is perhaps not too surprising when we're upgrading thousands of assets across the catchments compared to the baseline case we originally determined which events were critical. But even then, these results can usually be corrected so the full data set remains accurate. And taking this another step further, in the most complex cases where there's a need to make major changes to the network to resolve, say, large flooding issues, as well as reducing the spill counts, we found it most efficient to run these kind of studies in 2 phases. So first of all, we'll solve the most complex aspect, which is often kind of catchment-wide flooding problems, alone, just using fast-running design events to find the best solution to flooding. It's the fastest way to solve that most complex problem. And then we'll base the extract events, rather than perhaps on the original baseline, on the best result from that initial stage once we've dealt with the wider flooding issues. This way, the extract events are based on the closest states to what the final solution will be, improving that final accuracy. Then we can run the optimization again, solving for spills as well as flooding this time. Of course, the algorithms can learn from the full results from that first stage of optimization, which gives it a significant head start and minimizes the number of designs we need to run on the longer runtime designs which need the extract events as well as the design storms in that second phase. And then once we've done that, we can again run those final back checks as before. Now let's take a look at each of those stages in a bit more detail, perhaps beginning with the definition of the optimization problem. It might seem a little perhaps daunting initially to try and think of everything we need to include up front, but in several projects with various water companies now, we've successfully used a pro forma document to make this as straightforward as possible. This is just a set of tables which are filled out with all the required data, and it just helps to walk a modeler through the kind of optimization thought process required. It also helps to add to the robustness and auditability of these studies. It just keeps that record of all the options that have been considered. And I suppose the key items that go in here are basically a list of all the flood and spill and other performance requirements in one set of tables, a list of all of the various feasible upgrades in another, and generally this is quite easily generated by some sort of standard GIS-based processes. For example, just checking for pipes that aren't under buildings or nodes where there's some green space available to add storage or whatever. And of course, there's less need to worry about any items where one's not particularly sure if they'll be beneficial or not. In most projects, we've now developed simple screening methods and scripts we can apply later on to just filter out the items that aren't of any use before we actually run the optimization itself and maintain the efficiency of the process. And the final item obviously being some cost models to allow us to develop full costed solutions. So next comes the creation of the extract events from that full either typical year or perhaps 10-year event that's too long to include in the optimization directly. So simply what's done there is we export the time series results from that simulation into the Excel VBA tool we've created, which then produces suitable extract periods for us to use, as shown in that example there. For example, if the aim is to achieve perhaps 10 spills per year to CSO, we might select the 11th ranked spill, and then when the optimization would solve that, it will leave 10 other spills remaining. It ensures there's clear dry time before and after the actual spill event, as you can see there, which just allows for perhaps any changes in upgrades in the network that might cause that spill to move forward or backwards in time a little bit. And if possible, it'll avoid any long multi-day events, but otherwise it'll make sure it captures the full duration of those. If we have many locations across the network we need to be monitoring, then we might need multiple extract events. Typically, we find that 3 events is sufficient to cover all the CSOs, even on large catchments, as we tend to see a few clear patterns with several locations having similar kind of ranked rainfall events for them. Now, with the time periods established, we'll set up the template runs for the optimization to then edit. These will include usually initial state hot start files to capture the antecedent conditions, which has so far in most cases proved accurate enough despite widespread upgrades being applied across the network. And then as a final step, before we spend significant time actually running the optimization study itself, it's often worth just validating the stability with some bookend runs. So this just means we apply a few key combinations of upgrades and we run the extract event and the full or partial full time series and just check the results are sufficiently close before proceeding any further. Now, with the events to run set up, the simulation model itself is parameterized and we build the logic that must be followed per each design into what we call a workflow, which just defines the processes to be followed in sequence in each design. In many software packages, this is shown graphically, which also helps to form part of the documentation of what was done in a visual and easy to understand way. It also allows different projects to be very standardized, as it's always just building any new functionality on a standard template. Then, of course, we come to running the optimization study itself. And again, just in case there's some here perhaps less familiar with optimization, your typical results might look like this. So there's normally a usual way to perhaps show this is on a chart comparing the 2 competing objectives that the study is trying to achieve. Usually trying to minimize some particular network performance objective and also minimize the solution cost. So often we'll start off perhaps where the blue points are with an initial design of experiments, just trying to sample all of the various options available to optimizer. From that, it then learns which options are particularly good and beneficial and breeds those together to progress to solutions of a lower cost and a lower performance until we get a Pareto frontier forming. Pareto frontier just means it's the most cost-effective solutions, the optimal ones. And when points begin to cluster, you can see the argument is struggling to get any further. Then we've got some good confidence that's as far as it can possibly get, and that is the true most cost-effective solutions available. There's a couple of key factors to consider when setting up this kind of study to run. The first is that it's a multi-objective optimization. We want to simultaneously solve for both our performance objective, whether that be flooding, spill count, FFT, detriment, at the same time as trying to reduce our total solution cost, because this is what gives us that trade-off between the two. And secondly is the importance to get the most advanced, most efficient algorithm possible. From our experience in several engineering sectors, the applications of optimization in the water industry are by far the most complex, with far more input parameters, i.e. every upgrade parameter, than traditional applications in other sectors. And of course, as simulation times get longer, it's ever more critical to reduce the number of design iterations, i.e. simulations required to explore all of those combinations of different input parameters fully. Because of this, we prefer the use of standalone generic optimization platforms connected to hydraulic simulations via a custom API, as it gives us the free choice to use the best algorithm available at any time. And with the software we currently use, even the most complex problems are typically solved in around 1,000, 2,000 iterations, and so total simulation times up to around 1.5 hours per design are acceptable, and just keeps the total study run times to a few days. It also means you can run these types of studies on your own system without the need for specialist hardware if you have the optimization expertise. And of course, it's not just the runtime. Some algorithms will get stuck and they'll never converge on the true optimal solution, even if you leave them a very long time. For example, see this benchmark we've done on a test catchment. showing the difference between two algorithms both presented as the best two software packages could offer. You can see that the blue method has not converged in the region by where that arrow is, by the kind of lack of increased density of points on that Pareto front, as we showed on the previous slide. And that's a bit of a warning flag if we only had the blue results on their own, that something might not be quite right. And of course, as soon as we add the yellow algorithm in there, we can see that, yeah, there's nearly a 20% higher cost for the solutions in that region compared to what you'd have if you use the yellow algorithm. And on a full-size catchment, that could be tens of billions of pounds of unnecessary investment. It's often interesting to take a look at some of the typical statistics that come out of studies such as this. We're often running several catchments in parallel, because whilst two are running, the engineer can be setting up a third. We're often looking at solving several different problems in the catchment all in one go. So we might be looking at perhaps the three main objectives for a single study being to solve the high-risk flooding, perhaps all the CSO spill counts down to 10 per year, and reduce the full flow to treatment as well, whilst also ensuring that the remaining flooding in the catchment gets no worse, as the sort of storm tank utilisation and often other constraints as well. To do that, we'll be solving tens of thousands of asset upgrades across the networks, with total costs running into the billions if everything was to be implemented, though obviously the optimizer finds the subset that actually is necessary of that. And solving thousands of individual flood and spill locations with millions of meters cubed of flooding and spill being removed. Per catchment, it might only take an engineer around 8 to 15 days of their time to complete the study, whilst the algorithm is actually evaluating up to 10 to the 50 or often way more than that potential option permutations, different combinations which is possible, and being able to evaluate all those different items within 1,000 or 2,000 design iterations, like simulations. It really is quite impressive how efficient these algorithms are in minimising the number of simulations needed now. So now for the exciting part, let's take a look at some examples of the types of results from this kind of study. And perhaps the simplest way to show these is screenshots directly from an interactive reporting tool web app that we use to interrogate and understand the datasets produced. And I suppose to provide the context, I've left all the surrounding buttons in there as well, so you can imagine yourselves perhaps how you might use something like this. And I suppose the place to start is usually the trade-off chart between two or more key objectives. For example, here we have the performance, properties at risk of flooding, versus the total solution cost to achieve that level of performance, where each dot on the chart represents a single solution. It's an actual combination of upgrades throughout the network that have been simulated to determine what that performance and cost is. And here you can see we have three data sets, in this case representing different performance levels of the spill from CSOs, in this case each from a separate run through of the optimization. So in blue we have the case where we're just solving flooding only, then red is where we're achieving 10 spills per year, and green where we're trying to get a bit further to 3 spills per year. So the key feature is that left hand edge, the Pareto front, the most cost-effective solution to achieve any level of property risk and spill. And you can see here that thousands of solutions have been trialled, and as the points have begun to cluster at that left-hand edge, we have the confidence that this is as good as it's going to get, and there's no further what-ifs to try, perhaps unless we to go back to the start and add completely new options to the mix. It's perhaps most useful if we just keep the optimal points from that left-hand edge to make things a bit clearer. It can often be valuable to examine the gradient of these fronts. In this case, the cost to solve each sort of next property, and specifically where that gradient might change. It's quite frequent that we see sharp corners in the gradient indicating a change in solution theme, being required to improve performance any further, or perhaps just the exhaustion of the cheapest solution option type. It can also be useful to examine the change between different data sets. We can see clearly how much achieving 10 spills per year costs, comparing the difference between the blue and the red fronts. And again, we can see perhaps the risk to the business if the regulation was to tighten a bit further and then require perhaps 3 spills per year to be achieved, the offset between the red and the green fronts as to how much extra that might cost as well. Next, an invaluable chart is these option prioritization heat maps. It's a kind of key visualization of the relative importance of upgrade options throughout the catchment. So we begin by selecting which designs from our trade-off chart we're interested in. So select the cost and performance range of interest, and typically then just the Pareto designs within that range. And then we can calculate the percentage of designs which actually make use of each solution option that was made available to the optimizer. And then plot this as a coloured heat map. So the red areas where we have 100% of all of those Pareto designs requiring that option. So these obviously form your no regrets set of options, which are essential for all solutions, regardless of which particular combination you might pick to go with. So those can be prioritised for building first of all. Perhaps orange and yellow areas are useful, but not essential in all cases. They might only be needed in the higher cost range of your kind of selected cost performance region. So those might be the next items to consider building after a perhaps more detailed check. And then perhaps the green or grey items, they're not used in any designs or very few, so they're probably relatively high risk or can be discounted as an option entirely. It can be very valuable to compare between cost performance ranges, so create one heat map which might present the best options, say for up to £10 million worth of investment, which might represent your spend in the current 5-year investment period, but then make a check against the heat map for, say, the £50 million investment, which you might want to spend over the next 25 years. You can check that your actually 10 million solution, that all the planned interventions that shows red there are also red in the future case, and therefore you can be confident they are no regrets options. If you perhaps see options which are very important in the near future, but then as time goes on and more investment is provided, they become less important, then those should be considered very carefully. Of course, the idea will be to run multiple optimizations to accurately cover the future scenarios, rather than perhaps just extending the cost range a bit. And I suppose this then forms the beginning of down the path of the true adaptive pathways approach. The actual effort involved in setting up an alternative scenario is usually minimal, in sort of minutes range. It's just switching the settings within the optimization workflow. You don't usually need to build anything from scratch. It's just more computational resources to execute it. But yeah, this is really getting into another topic for another webinar. So yeah, we'll probably leave that there. And then perhaps for the next level of detail, it can be useful to inspect individual solutions on a map too. So if we were to select a point on our trade-off chart there and see what assets are actually contained within it, and then you can kind of see the build out of assets as the solution costs increase. So one would hope to find several lower cost optimal solutions which form parts of your kind of optimal end goal solution as the cost slowly builds out, with no additional upgrades within that becomes redundant. That's not necessarily always the case. And yeah, you can take any one of these solutions forward just as a starting point for perhaps the next stage of detailed design, which can give a big head start to the sort of detailed design teams and allow them perhaps to cope with the increase in future workload that's expected given the planned significant increase in the amount of investment required over the next few years. It's likely when looking at the heat maps or these selected solutions in detail after the study has been run that one will begin to find assets that cannot be upgraded for whatever reason, or other additional performance constraints that weren't known when the study was originally set up. It's not worthwhile doing a detailed feasibility assessment on every asset in the catchment at the start of the study when you're selecting all your options. It just makes more sense to run the study, find what is hydraulically important, and then go and do your more detailed feasibility assessments. So yeah, it's kind of inevitable these concerns will only be found at the end once the results have been run. So say, for example, we're in a meeting with some stakeholders and we find that a particular SUDS area removal option will be particularly challenging to build, let's say this region here. Well, as the optimization has run large numbers of designs, it's likely there should be several alternatives already available in the dataset which don't require that particular asset. So we can use this reporting tool to apply a filter to take that option out of the set of results and show what's left. And that's what can be shown on the cost versus performance trade-off chart again. So designs in bold are still available to us. They do not make use of that particular upgrade, whereas designs shown fainter in the background colour there do require that asset and are no longer available. Now, usually there should be other designs available. It might just be that the region becomes a bit more sparse, or it might be, as in this case, that option was actually quite important to achieve below around 200 properties at risk, and there'll be a significant kind of additional cost, perhaps from where our previous optimal front was around here to perhaps the next best solution available here. And okay, we might just accept that slightly more expensive solution, or it might prompt us to go away and say, could we get the same hydraulic benefit as that original option, but by an alternative way? Is it actually worth spending a bit more to achieve that? Is it still less than the other next best solution available in the original dataset? Now, the same case can also be applied to additional performance constraints. If it's decided later that it's essential to solve a particular flood location. Now, of course, if you apply too many constraints all added up together, you might run out of solutions that satisfy them all. But if that's the case, then it's usually quite simple to just add those constraints into the original optimization workflow and just extend it a bit with a few more designs with those targets in there. Now, once a few catchments have been run through these processes, one can begin to gain further benefits. I suppose firstly by comparing the relative cost effectiveness of different catchments in the business can assist in perhaps demonstrating the best use of limited funds and where they should be allocated. For example, here, if we swap the axis of our trade-off charts around, so it's the properties solved versus cost, so different catchments are perhaps starting at the same 0 point, and so all the lines should be equivalent. One may then see we might want to prioritise spending on perhaps the blue and grey catchments where the most benefit can be had for each pound spent, and maybe just do the minimum legal requirements on the other two. Of course, there's many other metrics which can be applied here. You might want to prioritise catchments, for example, where solutions make most use of green infrastructure efficiently. Or similar kind of charts can be used to generate accurate efficiency metrics, which can then be applied to other catchments in the business where it's perhaps not worth doing a full study. For example, here we might want to have a look at how much storage or equivalent is needed to solve each meters cubed of flooding or spilling in optimal solutions from 4 catchments. Obviously, the more catchments you add to this, the greater the accuracy in both the average value and the perhaps statistical spread in those values. And then, if we had a low risk catchment and we need to estimate the solution cost, we could simply apply, work out the meters cubed of flooding and spilling there is from a simple impact assessment, and then perhaps apply this metric to it to work out roughly how much storage we might require. If it's such a low risk to the catchment, it's not worth a full optimization study on its own. Now, before we get ahead of ourselves much further, we do need to remember that any data set based on extract events has the potential to differ from the supposed correct result from the full 1 or 10 year simulation. Though those extract events may be accurate for the baseline case used to select those events, where it should match exactly, these solutions have applied large numbers of asset upgrades throughout the network, so the performance might change. We might have some issues due to the antecedent conditions changing, because remember, the extract events use an initial state file, but that initial state file remains static from the baseline case. Or it might partially also be due to perhaps the worst day for a particular spill might shift to a different rainfall event in the year. So, having selected a few Pareto designs we're particularly interested in, it might be those we're just most keen to take forward, or it might be just a wide spread across the full cost performance range as here. We rerun those on the full time series simulation, and we can then plot the comparison. So for a study such as this example, where all the spills must achieve 10 spills per year, but the flooding performance is a kind of variable optional extra, if you like, it's perhaps useful to plot the property risk versus cost trade-off chart for both cases on top of each other. And yeah, if we assume relatively small deviations in spill performance that could be taken up with a bit of local storage, we can apply a bit of a cost offset to the time series results to account for this. For example, if we take this point here, which is predicted to cost around £50 million from the extract event alone, but then if we rerun it on the time series event, it shifts slightly to the right, a slightly higher cost, as the time series has predicted some slightly more severe spills, and so some additional cost is required. For most cases we've seen, on the scale of the total solution cost, these discrepancies are very small and often points directly overlay, as you can kind of see on the low cost designs here. However, this chart is perhaps more typical of the worst differences we normally see, just to demonstrate the point of what the offset is. And often the offset is relatively consistent when it is there, so it's usually a simple matter to extrapolate that offset and correct the main optimization dataset accordingly, so we still have a high confidence in the full result set. Okay, so I think that's probably all of the different typical result types that can be shown. So now we can move on to perhaps a summary of the outcomes and benefits of this kind of approach. Beginning with the outcomes of the study, obviously firstly, all possible upgrades across the catchment can be considered together and holistically. So aside from completely new bypass sewers or things we just didn't think to include up front, there's nothing else that really could be done, and all options have been given a fair chance, competing on cost to form part of that complete solution containing all the different types of upgrades together, and solving all of the potential issues in the catchment as well, even the perhaps smaller issues which traditional methods might have to ignore for the sake of time. And from this obviously develops full catchment-wide solution themes, with every potential solution fulfilling all the mandatory performance requirements. We've set up all the possible constraints we need up front, and every design can be shown to achieve those, or perhaps ones that don't label clearly. And obviously we've got the full range of performance versus cost, and we can choose where we want to be on that curve once the study is complete. And of course we can have a look across a range of other perhaps criteria or different scenarios as well, different climate change, different growth scenarios, etc. Just by the quick rerunning of the study. Obviously got the GIS heat maps, which give that quick visualization of the priority of each upgrade and those overall solution themes within interactive reporting tool as shown. And again, you can just look at whichever part of that performance and cost trade-off you're interested in. You get new set of heat maps. Supporting that, there's the database of thousands of individual solutions. You can go away, you can pick one to take forward to the next stage of design work. And from the kind of individual data points, we can create those high-level summary metrics, which can support that kind of high-level business-wide type planning things as we've just shown. So the benefits of some of those outcomes, I suppose, first of all, it's the confidence you get in what that optimal solution is. Just lowering the risk in any business plan. We've actually had some simpler local cases where modelers have some idea of what the likely solution is, but they still need this kind of data set in order to prove that to the regulators. So the main thing is, as we just said, there's no further what-ifs to explore. all the different possible combinations of all those option types have been explored by the optimizer, and you can see that you've got good convergence if you can see all those points begin to cluster on the Pareto front, and that's as far as it's going to get. Obviously, the no regret solutions are very clear from the commonalities across all the designs in that Pareto front, as shown on the heat map, and that just gives you your core path in that kind of adaptive pathways approach that regulators are trying to push for. So it's just a good first step along that method. Solutions are obviously catchment wide, they're strategic, and they're quite detailed, which again helps to lower the risk. You can gain some efficiency by solving all those isolated issues together, and given that it's perhaps a more thorough job, and more possibilities are being considered by the optimization, and so solutions it produces are closer to the buildable state compared to what you'd be able to do manually. There's just less risk of proposing the impossible through some very broad brush approach and then underestimating what that solution cost might actually be. And of course, you're also fairly considering perhaps some of the newer options, which perhaps in a manual method there's always some bias towards what a modeler is familiar with, whereas here the algorithms are equally unfamiliar with all these different option types. It's just considering them all quite fairly based on the cost, so it might assist with presenting some more innovative blue-green or nature-based solutions a little bit more. The workflow and dataset that have been generated here are also of use beyond perhaps the immediate study. They kind of form a company asset for future use as well. So initially you've got all those heat maps and those example solutions, which give a great starting point for the next phase of more detailed design passed on, and to allow stretch modelling teams to cope with expected increase in workload as investment increases in the future. Obviously, we've then got our sort of summary efficiency metrics, which can help supporting region-wide investment decisions about the level of investment required across the whole business, and also being able to compare between different catchments as to which ones are perhaps most efficient to invest in. And with all the data being generated up front in this kind of study and then being available in some kind of interactive live reporting tool, it really assists with collaborative planning. You can have that tool open in a meeting with all the stakeholders. You can be looking through those maps, finding all the potential issues and filtering them out live and seeing how that might affect your solution response, without having to perhaps stop, go away, do some offline analysis and go back later. Typically the level of solution we're looking at is generally an improvement on manual methods as well, solving more those smaller issues as well as the big ones, and usually getting better performance from that, and also in a much faster time frame. Just impossible to analyse all the different performance requirements that we're looking at here within a matter of just a few weeks with any other method. And then I suppose just having quite a specific look maybe at where the outputs of the study fit within the kind of business planning and then the future solution implementation areas. So kind of, as we said a little bit, in determining that business-wide level investment required, we can use our cost efficiency metrics from the aggregated results of several catchments to decide where to allocate funds between different catchments. We might be competing with the same budget. We can compare the gradients of those cost performance trade-offs, which one's the most efficient place to put investment, perhaps which ones make the best use of maybe green infrastructure as well. And I suppose for proving the cost effectiveness of going above and beyond legal minimums, we just have to look at the shape of our cost performance trade-off. Is that gradient steep enough that we've got enough improvement per pound spent to be worth spending a bit more than the minimum required? And obviously, to determine the high-level catchment solution strategies, we just have to look at the heat maps, which instantly show us visually where the priorities are, and that no regrets core pathway is. And then taking it further towards solution implementation, obviously we can look at the solution heat maps and the example solution networks as a good starting point for that detailed solution design and costing. Now to finish, I suppose just a quick look ahead at where we might want to go with this in the future. So obviously optimization is quite wide in scope, both and just within optioneering alone. It can be used on the kind of wider business planning cases here and the detailed optioneering work. And this specific novelty of including the spill count or FFT, those long-term metrics, has currently been well proven for those high-level business planning type studies. So next, it might be interesting to try it out on perhaps the more detailed optioneering level. For example, local CSO spill reduction schemes where an easy solution is not available. Obviously, as you get more detail, and the level of accuracy that you're approximating that spill count or the actual events needs to increase. So that's probably the first thing we'd quite like to try next. There's also the ability to add new performance criteria such as carbon cost as well as normal cost, and perhaps include some of the wider societal benefits of those green options so that they get favoured a bit more. Certainly we've had experience in the past with previous studies where we've had three objectives: performance, cost, and carbon cost, for example. So it'd be interesting to see what other performance criteria you might want to include there, or to have a look at adding in some additional scenarios. Taking a look at the different combinations of climate change uncertainty, demand uncertainty, how much housing growth might happen, what level of technological development might occur, which could get us a bit better performance out of the networks. Because obviously rerunning the study on a new scenario is minimal in terms of the engineer effort required, just a bit more CPU time to run it, but it's incredibly helpful in reducing the business risk required, and it's again just pushing us along the route towards a full adaptive pathways approach, where all those different scenarios have been looked at, and although with the methods presented here and the kind of analysis of the heat maps between different cost regions, you're beginning to get on the way to being able to analyse the pathways and determine the core pathway. We're also looking at developing a tool, and we've done some experimental trials already that's able to determine smart ways to move between the different Pareto fronts from the different scenarios, and to get us a lot further than the manual analysis of the results of this can, to kind of automatically assess the differences between those different Pareto solutions and create decision points where it detects significant differences. Again, I suppose it'd be interesting if anybody wants to further that to get in touch and perhaps work together on it. And with that, I think that's probably all there is really to cover in this sort of main presentation. So I suppose back to Karen to introduce the question and answer session at the end.
Thank you very much, Ben, for taking us through the advanced optimization methods. We're going to go straight to the questions, as we've had a few come through already on the topics that we've covered today. If you do have a question, please feel free to write that in the panel that appears on your screen, and we'll attend to as many as we can. So, Ben, the first question: can you optimize for a non-fixed spill target to get trade-off of spill count versus cost?
So with the current method we've been using, not directly, although you can get quite close to that by perhaps doing several kind of different scenarios, if you like, targeting different spill constraints. There was, if I can go back to perhaps this slide here, you could do something fairly similar to this, perhaps, where you can essentially have like a 10 spills per year, 3 spills per year, 1 spill per year, maybe 30 spills per year Pareto front, and you can see the cost differential between each of those. So yeah, you can't necessarily give you the full continuous perhaps spill count versus cost as a trade-off curve, but you should be able to get quite close to it using a method like that. And of course, there's always other ways of looking at this. You could just look at perhaps a correlation study between, say, a parameter from a design event or a storm pack event, and comparing that against the spill count up front. And then obviously running all on sort of event and be able to convert backwards. But that doesn't, I suppose, use the same direct measurement of those critical events as this does. So you might lose some degree of accuracy there. But yeah, it's an interesting one. Might be worth discussing further with us afterwards.
Thank you. And how long should a study take to run?
So typically we're looking at somewhere around 4 to 8 weeks, depending on the complexity of the number of outputs that are required, and the size of the model and how slow the model takes to run, with the runtime usually being around 2 to 4 weeks within that. So yeah, if you've got obviously quite a complex catchment with a lot of CSOs, then you might need more extract events to cover all those conditions, and it can take a little bit longer to set it all up. And similarly, if you've got a very sort of slow to run model, it might take up to that maximum limit of around 1.5 hours per design, and then it will take significantly longer than a small catchment, which might need say 15 minutes or so to run a design.
It may be better for us to cover this question on a separate call, but maybe Ben can give us an idea. The question is, how do you account for the antecedent conditions in short events? And do the extract events require a long time for the sum of interest to set up infiltration and similar?
So when we create extract events, we'll take an initial state file from that exact point in time at the start of the event from the full time series run on the baseline model. And that should usually be enough to capture the kind of long-term effects of how the runoff set up and ground infiltration or all that kind of stuff. And it usually seems to be sufficiently accurate for the purpose of these studies, even though obviously that initial state remains static on the baseline network, if you like, whereas upgrades are being applied within the event itself. Sometimes you can get stability issues with doing that, where it will just fail to run because there's been too many changes between the two cases. And in that case, we often find if we use a runoff only initial state, it will solve most of those issues. And in some ways, we're beginning to think that actually a runoff only state might be the more accurate one to use anyway, because the long-term stuff gets taken for the initial state file, all the runoff type parameters, but the perhaps short-term items that are perhaps more variable when the network's changed get taken from a new initialization. So if pipes have been upsized, then it kind of corrects the depth a bit better. There's still be a bit of investigative work to do there to establish which one is the best, and we'll probably keep using our existing method of the full initial state file where we can for the moment, perhaps until we're looked into that a bit further.
Another question that we have here is, can you use a 100th once spill from a 10-year TRSR, as this can be more reliable?
So yeah, absolutely. I don't really see any issues or changes to the method needed to include that. I suppose it might take a bit longer, I suppose, to set a study up if you've got to run a 10-year time series event up front before you can decide those extract events. But if you've already got that run somewhere, you can just extract the time series results directly and pass that into our method anyway. So in that case, it probably wouldn't be too much of an extra issue. It might just mean that the back check phase takes a bit longer to run all those designs through. But again, you get to that trade-off, isn't it? And then you get a perhaps more reliable result that's a bit better statistically because you've got the average over the 10-year severity rather than just the 1 year.
Just a couple more questions to get through, Ben. What level of deviation is typically found when back checking still counts?
So I suppose that the worst case of deviation is as shown on the slide. on this slide here. So you can see that there is also generally comparable, and there's a fairly consistent offset that might need to be corrected for when you do the back checks. But typically, if you're looking at it on this kind of metric where it's a cost difference to correct for the spills, I think the worst case here was around about 10% of the solution cost. Often you get much closer matches than this as well, more similar to the points you've got in the top left there, where they pretty much directly overlay. I suppose it just depends very much on exactly how that catchment works and how the hydraulics affect things.
Another time-related question, how long can the simulation times be?
So I assume this means how much simulation can you run per design. So the general rule we tend to work to is an absolute maximum in terms of real-world time that it takes to run of around 1.5 hours per design, because obviously you have to run that to 1,000 or to 2,000 designs to get the full Pareto front. You can obviously do some degree of parallelization, but not you can't run them all in parallel. So I suppose within that we'd typically be looking at, let's just take for example the worst case largest catchment with the most complex outputs that might go into that. So you'd probably have like a design stump to look at flooding. That might be 1 day duration. You then probably have 3 spill extract events, say each 3 or 4 days each, and then maybe an FFT extract event as well, which normally needs to be a bit longer, say maybe 5 to 7 days. So overall, you're probably looking at about 20 days total simulation duration, which would then give you that 1.5 hours maximum per design runtime. Obviously, you probably want to get a bit less than that to keep the total study runtime down. In that worst case, your total study runtime, just literally the CPU time running the study, would probably be around about 4 weeks in total, which is as long as you really want it to be in order to get a result back in a suitable time frame. So obviously, if you've got smaller catchment though, it's generally not too much of an issue. But in big models, you obviously need to keep in mind what that total simulation duration is coming out at.
And I think this is the last one we'll be able to cover. We have uncertainty in the models when it comes to predicting spill counts, which do not align with the EDM data. Can this obtain higher accuracy?
I don't think this method will help with that specific problem. For these kind of catchment-wide optimization, sort of optioneering type studies, we have to take a base model and assume that is the source of truth. And basically whatever that model predicts is what the result of the study will be based on. So if that model is incorrect, then I suppose it will produce slightly accurate results as well. However, optimization can help with tuning a model, but in a completely separate type of study to this. So we've done a lot in the past trying to verify models against flow monitor data, and I imagine it should be a fairly similar case to take EDM data as well as flow monitor data and run a similar kind of verification study where we tune various parameters within the catchment that are known to be a bit uncertain to get the best match to some real-world monitored data, which can save quite a lot of time over a manual approach, and particularly if you've got parameters where you're not really certain exactly what they do, which might be the case with some of the longer-term simulations where less prior verification work's been done, maybe. So I imagine you might want to do some kind of verification type optimization study first, and then once you've satisfied yourself that the model is then sufficiently accurate, then you could take it into this kind of optioneering catchment optimization study. But obviously the verification thing is a whole other topic, so again, it might be best to contact us afterwards, and we can discuss in more detail on that.
Thank you, Ben. So that's all we have time for. I'm sorry if we didn't get a chance to answer your question, but either myself or my colleague will come back to you with an answer. I want to thank you all for attending today's webinar, Advanced Optimization Techniques, Managing Spill Count and Risk with Confidence. I hope you have found today useful and informative. And just before we go, thank you again, Ben. That's it, everyone. Thank you very much. See you on the next webinar. Enjoy the rest of your day.